Good morning, everyone. Okay, we are coming to the fourth lesson on acids and bases. So this part will be on the pH scale and indicators. Okay, as well as a little part on how do you select the right indicators for a titration setup. All right. Of course, later on we will recap on what's the titration setup, okay, and then maybe like you view the whole titration process once again just to refresh your memory. Okay, so first of all, pH skills and indicator okay, so basically this part potency. Okay, oh no. Okay, what do I mean by potency okay, so basically how to measure, okay, how acidic or alkaline a substance is. Okay, we go by the concentration of H plus or OH minus in water. So in the previous lesson, okay, I think the previous three lesson, okay, you know that there's a certain number of factors they will affect this concentration of H plus. Okay, one is of course the concentration of the acid, which is different from the concentration of the H plus. Okay, and then you have strength of acid, okay, which is the degree of dissociation, okay, whether dissociate fully or dissociate partially. Okay, then you also have the basicity, okay, which is the maximum number of H plus ions that can be dissociated per molecule of acid. Okay, so under strength, just to recap, you have strong acid or weak acid okay, strong means those that dissociate fully, weak means those that dissociates partially. Okay, so this one is dissociate fully. Okay, so these are important concepts that you need to grasp okay, before this lesson this one means you dissociate partially, which usually gives you low concentration of H plus. Okay, and then you have basicity. Okay, so under here you have things like monobasic, that means can dissociate 1 H plus per molecule of acid. Example is like HCl. Okay, you also have dibasic, which is your H2SO4. So that is 2 H plus per molecule of acid. Alright. Okay. Then of course you have tribasic which is not often seen. Alright. Okay. Okay, let's go to how the concentration of H plus is related to a pH. This might look a bit complicated, but this one is actually outside your syllabus lah. Okay, just for your information only. Okay, outside syllabus, just FYI. Okay, but basically the point of me putting this here is to tell you basically the lower the pH, the higher the concentration of H plus. Yeah, just to show this relationship lah. Okay, or sometimes next time if you still take chemistry at higher level, it will tell you negative log. This is a symbol for concentration of H plus. Okay, equals to the pH. Okay, pH is the negative log of the concentration of your H plus. Yeah. Alright. Okay. So the pH of a solution can be determined by using a pH meter. Okay, so usually it can be measured using a universal indicator and then comparing the color of the results against the color chart. Alright. Okay, so it's a set of number from 0 to 14. This one being 0 being the most acidic lah. Okay, 14 being the most alkaline. And right at 7 is neutral. Alright. Okay. So anything less than 7, is acidic lah, basically. And anything more than 7 is basically alkaline lah. Alright. Okay, so it's not like the higher it is, the more acidic lah. Alright, okay. So this is your pH scale. Okay, so acid, okay, pH less than 7. Alkaline, pH more than 7. Neutral, exactly 7. Okay, as what I have mentioned earlier on. This one quite straightforward. Okay, then okay, then you also have the indicators as well as their pH range. Okay, so maybe I can pause a while, let you have a look at what's a universal indicator lah. Okay, because that one actually shows a lot of colors. Yeah, the colors of universal indicator is here lah. Alright, okay, I just let you have a look. Okay, so universal indicator actually comes in okay, is this form lah. Okay, either a paper or the die form. Okay, both we also have. Okay, so I can show it to you lah when I'm back in classroom just to let you have a feel of the real thing. Okay, so basically after you dip it inside the sample that you want to test, you compare it against a chart. Alright. Okay, so I have one okay, whereby there's a chart on the container itself. Then you can test out on your toothpaste. Okay, last time I even been bleached to classroom, okay, for students to try, but it gets quite messy. Okay, then you can compare it against the universal indicator chart. Okay, so other than universal indicator, there are other indicators, okay, such as your metal orange, screen metal orange. Right. Okay, so they all have a certain range of pH at which the indicator change color. pH range at which indicator change color. Okay, so for example, metal orange changes color at 3 to 5. So that part, it will look orange. Yeah, then screen metal orange also again changes pH from 3 to 5. So that part, it will look gray color. So anything less than 3 is violet for screen metal orange. Okay, anything less than 3 is red for metal orange. And then anything more than 5 is yellow for metal orange. And then screen metal orange, anything more than 5 is actually green. Then here and there you have other phenolphthalein, which is actually seldom in use these days. Okay, as well as dimethylene. Okay, that one I think got appear in, I think, year 2020's O-level practical. Yeah, something that we don't usually use. Okay, but okay, what you need to really know is that the color at which the indicator change color. Okay, alright, so before that, maybe let me recap to you okay, what's a titration setup. Okay, so titration setup, normally you have a retort stand, something like this. Okay, just on a diagram just to show you. Okay, then you'll put a conical flask. This one clamp onto your burette one. Okay, alright, so this one is your burette. Okay, then inside, okay, usually one acid, one alkaline. This one can be acid or alkaline. This one, then if acid is in the burette, then this one usually I'll put alkaline here. Okay, then your pipette. Okay, we will let you have a chance to have a feel and do titration. Okay, it's one of those very standard skills that you must have as a pure chemistry student. Right, standard practical skills that you must have as a pure chemistry student. Okay, so the setup looks like this. Okay, so then you will add 1 to 2 drops of indicator at the start before you add anything from the burette, and you monitor the color change. Alright, okay, so just as a recap, okay, over here, let me show you how they do the titration once again. Okay. Okay, we are. Oh no. Okay, what happened? Okay, never mind. Let me restart my OneNote. Hang on. Okay, it's here. Right.
Okay, this is a video on preparing sodium nitrate using titration. So first of all, you have to measure 25 cm cube of sodium hydroxide using pipette, and then after that transfer it into a conical flask. This is a
Okay, so this case is the alkaline inside the conical flask in this
filler
video.
bulb to suck up the sodium hydroxide solution into the pipette.
So this is how
This
you
pipette is
set up
25 cm cube.
pipette.
Now it's quite difficult to operate the filler bulb, but you have to learn. Okay, then after that you are ready to suck up the sodium hydroxide solution from the white bottle into the pipette. Okay, and now is to transfer the 25 cm cube of sodium hydroxide in the pipette into a conical flask.
Okay, so now he will transfer the solution from pipette to the conical flask and then add in the indicator.
Now this is an acid alkali titration experiment. The acid is nitric acid, the alkali is sodium hydroxide. When these two reagents react, they would form sodium nitrate as well as water, and the sodium nitrate is the one that we want. So sodium hydroxide in the conical flask. And step 1B is to put 2 drops of methyl orange indicator into the sodium hydroxide solution. Take note of the color of the methyl orange. Methyl orange, its color is actually, of course, orange. When it is neutral, it is orange. When it is in alkali solution, it is yellow. See, it is yellow because sodium hydroxide is an alkali. So using a white towel, you can see the color clearer. It is yellow. And in acidic solution, methyl orange is actually red. So methyl orange is actually red, orange and yellow. So right now what I'm doing now is to fill up the burette with nitric acid. So you have to fill it up using a filter funnel, and then after that you have to run nitric acid into the conical flask until the solution permanently changes to orange. That means when it is neutral, when nitric acid exactly neutralizes sodium hydroxide. That means when the solution in the conical flask is neutral. And once it is neutral, you have to record down the volume of the nitric acid needed to neutralize sodium hydroxide. So the sodium hydroxide is 25 cm cube, and at the end of this experiment you should have the volume of nitric acid. See, it changes to orange.
So you will add the nitric acid slowly until it changes. One drop of the nitric acid changes the methyl orange to orange. Alright, okay?
Okay, changes to orange. So at this point you should record the volume of the nitric acid, and using the volume of the nitric acid that you record as well as the 25 cm cube of.
Alright, so that's the end of the titration. The rest is salt preparation. Okay, so after you do a titration, okay, if you monitor it using a data logger, and then you get some sort of what we call a titration curve. Looks something like this. This one is a bit, there's two rapid pH change. Okay, sometimes it's just like that. just it can be this way, one rapid pH change. Okay, so you have pH and then the volume of acid lah or alkaline added. Okay, so there's a couple of things to look out for okay, in a titration curve. One is this part, okay, whereby it tells you the initial pH, okay, of what is inside the conical flask. Okay, so for example, it's an alkaline, it should be something that is more than 7 lah. Okay, this case if it's something like the one I have in green, okay, pH let's say is 1. Okay, so it will be a acid inside the conical flask. So this is the initial pH. Okay, then after that, as you add okay, so this case is alkaline inside conical flask. So you add, then the pH starts to drop. At a certain point, it drops very rapidly. Okay, so the concept here is what? What's the concept? Is that the pH range for color change from the indicator must be within the rapid pH change. Okay, what do I mean by this? Okay, so let's look at this carefully. Okay, maybe green. You look at this is 10.4. Here is 8.4. Okay, so this part versus the second rapid change here will be around, let me see okay, just roughly lah, this kind don't have to be so precise, 5.6 to 2.4. okay, alright, so there's two rapid pH change. So you see we use phenolphthalein, okay, for stage 1. Okay, why is it so? Because if phenolphthalein, you see, is 8 to 10. Okay, it's within 8.4. Okay, so stage 1 let's call this stage 1 and then this is stage 2. Okay, so the stage 1 rapid pH change is from 8.4 to 10.4. That's your rapid pH change. Okay, so the concept here is to choose an indicator whereby it changes color within this range. Okay, that means something like phenolphthalein, 8 to 10 phenolphthalein pH range at which it change color. So phenolphthalein change color between 8 to 10, so fits within the rapid pH change of 8.4 to 10.4. Okay, so how you answer is like that. You need to quote the value. pH range for color change 8.2 to 10 falls within the rapid pH change of stage 1, which is 8.4. Okay, so stage 2, then you have to choose something like metal orange. Stage 2 will be 3 to 5 kind. Okay, metal orange. Okay, stage 2 use metal orange will be good, because otherwise if you use it for stage 1, it will just stay as yellow, it won't change color okay, because it only changes color within here, right? 3 to 5. So anything more than 5, it will actually stay yellow, right? So it completely missed the rapid pH change, which is the point at which the acid neutralizes the alkaline. Okay, you stay yellow, you won't change color. So you want phenolphthalein, then you can change color. Okay, from pink to colorless from 8 to 10. Yeah. So how you answer is that the pH range for color change is for metal orange 3 to 5, which fall within the range of rapid change for stage 2, which is 2.4 to 5.6. Yeah. Okay, then comes universal indicator. So 0 to 2 is red, which is usually a strong acid. 3 to 4 is orange. 5 to 6 is yellow. 7 is exactly neutral. 8 to 10 is, okay, I change this to blue. Okay, and then 11 to 12 is indigo, something like purple, and then violet from 13 to 14. Okay, so what it means is this. Okay, so usually the lower the pH, right? Lower the pH, correct. Okay, the higher the concentration of H plus. Okay, higher pH, lower concentration of H plus, higher concentration of OH minus. Yeah, so 7, remember just now we discussed, is exactly neutral. Okay, anything less than 7 is actually acidic. Anything more than 7 is actually alkaline. Okay. Okay, doesn't mean no pH though lah. Higher concentration of OH minus does not mean no H plus. This one, higher concentration of H plus doesn't mean no OH minus. Okay, it's just that here you got high concentration of H plus, very low concentration of OH minus. The other side, very low concentration of H plus, very high concentration of OH minus. Okay, that's what actually it means lah. Alright. Okay, so this one is once again a recap okay, of how the 3 different factors, okay, strength, strength, as well as basicity affects pH. Because all of them actually affects, if I want to change this flow chart size, affect the concentration of H plus, which in turns affect the pH. Okay, you must be able to link all this. Okay, so concentration of acid is basically the number of acid that you dissolve. Okay, the amount of acid that you dissolve in a given volume of water. Okay, so it could be 2 strong monobasic acid, HCl, HCl. Okay, one I put 0.02 mole per dm cube. The one I put 1 mole per dm cube. Okay, of course this one will get a higher concentration of H plus which means the pH is actually lower lah. This one lower concentration, so the pH actually higher lah compared to the 1 mole per dm cube one. Okay, that's one factor that affects concentration of H plus and in turns will affect the pH. Okay, then we come to strength. Okay, strength, you have strong or weak. Okay, let me just pick an example. Okay, ethanoic acid, okay, versus something like HCl. Okay, because both is monobasic. Okay, good comparison. Okay, so ethanoic acid I shall simplify to something like this. Okay, actually all this this one means partially dissociate. This thing, this weird looking double headed arrow. Okay, A minus okay, then I have something like HCl, one headed arrow, fully dissociate. Okay, so I say this one I got 1 mole per dm cube, but because partial dissociation, so little. Okay, versus HCl, I got 1 mole per dm cube, but 100% fully dissociated, so I get 1 mole per dm cube. So you can see this one, the concentration okay, is actually wait, sorry, you can see this one okay, sorry, you can see this one how strong okay, you can see this one okay, this one again the concentration is higher, or concentration of H plus, so the pH will be lower, but this one the pH will be slightly higher. That's why weak acid always like around 3 to 4. Okay, alright, so you must be able to link the idea of strength to concentration of H plus, and then in turn link it to the its effect on the pH. So 3 things to link together lah. Okay, so there's a very interesting question from 2021's O-level question on basicity, strength, okay, and concentration of acid and how they affect the pH. Okay, that one important question to look at in assignment 4A. Alright, so do watch this video before you attend 4A. Okay, next thing is basicity. Okay, basicity works this way. Let's say you have ethanoic acid again. Sorry, I don't have ethanoic. Shall use both strong one. HCl. Okay, monobasic this case. That means 1H plus dissociate per molecule of acid, then versus something that is also strong but dibasic, sulfuric acid. So you get 2H plus down here. Okay, so what you get is this one. Remember, mole per dm cube is the units for concentration. But this one, if I have 1 mole per dm cube, the concentration will be 2 mole per dm cube. Okay, so this one, of course, I expect the pH to be lower lah, because higher concentration of H plus. Okay, so that's how basicity can affect pH as well. Okay, let's look at some of the true false question and then one example on your titration curve. Okay, right. Okay, so we can measure the pH of a substance using litmus paper force. Okay, this one you can actually do using data logger. The best you have to have a data logger is the best. It's really exact one. Okay, otherwise universal indicator. Okay, litmus paper just tell you acidic, alkaline, or neutral. Nothing much. Okay, so this is false. Okay, the lower the pH, the higher the concentration. This one true. Okay, I already tell you this relationship very clearly. Okay, so I hope you can take note of this thing. Okay, wait, hang on. Take note of this thing. Okay, mixing solutions of pH and 2 and 4. Okay, will produce a solution of pH 3. That's not how it's calculated. Okay, because remember, if you really want to show, I can show using this formula. Okay, right, because pH 2, sorry. Okay, pH 2 the concentration of H plus tend to about of -2. Okay, then pH 4 concentration of H plus equals 10 to the power of -4. Okay, so obviously when you combine them, the pH 3 means concentration of H plus is 10 to the power of -3. Obviously they are not Okay, so 3 is wrong. Strong acid, okay, strong and concentration, they are independent factors. Take note just now. Okay, they don't affect each other. That's why I put a cross down here. Okay, so that means the strong acids doesn't equal to concentrated. I also mentioned in I think lesson 2 or lesson 1, I think. Okay, doesn't equal to okay, so that's false. A dibasic acid always has a lower pH. Okay, need not be, because you also have to depend on strength. You also have to depend on concentration of the acid itself. That's not the sole factor affecting the pH. Monobasic acids are weak, dibasic acids are strong. Okay, basicity has nothing to do with strength actually. Okay, they are not related at all. That's why this is false. If concentration of the same acid, number 7, if concentration of the same acid is increased, its pH will decrease. Yes, because for the same acid, the concentration of H plus will definitely be more be it strong or weak. If the concentration of the same acid is increased, its basicity will increase. Okay, basicity is intrinsic natural to the acid so concentration, okay, doesn't affect basicity Okay, basicity is the total number of H plus dissociate per molecule of acid It's false because never say per molecule of acid. Okay, right. Okay, let's look at an example. Okay, on the titration curve. This is actually used to be an O-level question quite some time back in 2010. Okay, let's have a look at what is happening. Okay, so a pH probe attached to a computer measures pH changes during some titration experiment. Okay, so what happens in this experiment is that 0.1 mole per dm cube of hydrochloric acid, HCl, okay, is actually added from a burette. Okay, concentration is like that to a conical flask with 25 centimeter cube of sodium carbonate. right? Okay, and see is what happened. It happens in two stages. Stage 1, sodium carbonate reacts with dilute hydrochloric acid, okay, Na2CO3 plus HCl. It says gives you a neutral salt and sodium hydrogen carbonate. That's sodium hydrogen carbonate. Neutral salt should be NaCl in this case, okay? Because you need to balance the Na and the Cl lah. So that's actually the neutral salt, if you are wondering why. Okay. Okay. So then sodium hydrogen carbonate undergoes a further reaction. Okay. There's an E missing here. With your hydrochloric acid. Okay. Okay, so that's why you experience two rapid pH change. Okay, over here. Okay, so you're told methyl orange is an indicator. Is red in solution below 3 and then orange in solution above 4. So explain why the pH probe is better than the methyl orange for titrating sodium carbonate. Okay, so if you look carefully at this curve, okay, and there are two rapid pH change. This is what they call the step. Sometimes I call it a rapid pH change. Okay, so this part where the pH curve is vertical, this one is the what we call the rapid pH change. Okay, or sometimes O level use this term called step. Okay, the second one, or rather actually this is the first one, is 10.4 to 8.4. Okay, so this one is the first rapid pH change. Okay, and then initial pH is 11.6, which is correct because it's an alkaline inside the flask. Okay, so they are okay. So how you answer this? How come pH probe is better? Because methyl orange the thing about methyl orange is, okay, it only changes color from 3 to 5. 3 to 5 is here. Okay, you can only detect the second one. Okay, first stage cannot detect. It will stay yellow. Alright. Okay, so the first one from 8.4 to 10.4. The second rapid pH change from 2.4 to 5.6. So methyl orange only changes color between 3 to 4. So for the first what you call it, rapid pH change, it will remain, oh sorry, he will change this okay, to yellow. Alright, because the pH is still above 5, so it will stay yellow. Okay, so next thing is, what is the pH of the sodium hydrogen carbonate? That means the salt for the first stage. Okay, very simple. Okay, you take the average of the two ends of the rapid pH change. Okay, this is the salt of the stage 1. Okay, take the average of the top and bottom value, okay, in the rapid pH change. Okay, so what you do is this, you take 8.4 plus 10.4 divide by 2 lah. Okay, that's why how I get these two numbers from the titration curve. Alright. Okay, so next thing, what's the name of the neutral salt? Just now we already figured out. Okay, this one, sodium chloride. Okay, so this one formula is NaCl. Hopefully no issue. Okay, so sodium carbonate is described as a weak alkaline. Okay, but sodium hydroxide is a strong alkaline. So use information from the graph to explain why. Okay. Okay, so basically what happens is this. Okay, the pH of NaOH is around 13, while pH of your sodium carbonate, you can see is 11.6. Okay, it's 11.6. This one. Alright. Okay, so you gotta list the two lah. Okay, since your NaOH has a higher pH, it means it's a stronger alkaline. because it dissociates fully to give higher concentration of OH minus. Okay, remember higher pH, higher concentration of OH minus. Okay, while your sodium carbonate only dissociate partially to give lower concentration of OH minus. Alright. Okay, so then I think this is it. Okay, for the fourth lesson.